Here are a couple sample problems dealing with some centripetal force ideas along with energy concepts too. The first problem, we have a moon called Io. It's a small moon of Jupiter. It has an orbital period of 1.77 days. The center to center distance from Jupiter is 4.22 times 10 to the 5th kilometers. Find the mass of Jupiter. Okay, so what do we have there? We have a situation where we have Jupiter, and then we have this moon orbiting Jupiter called Io, and the center to center distance we'll call R. Okay, and it orbits in a time of 1.77 days. That takes 1.77 days to make one complete turn. Okay, so looks like we have a situation where it's circular motion problems, so that probably deals with the idea of centripetal force, huh? Remember centripetal force? The general expression for that, or equation, excuse me, is the mass of the orbiting object times the tangential velocity squared divided by the center to center distance. Okay, tangential velocity would be the velocity is tangent to the curve. Alrighty. Well, first of all, I can see here that we have days. That's not a very good unit. It's not in international units. And also kilometers. So we need to convert days to seconds, kilometers to meters. And I did this already here. You can see the time in days, 1.77 days. Now we'll just convert it over using the factor label method. Multiply by 24 hours per day. The days cancel. Then we'll multiply by 3,600 seconds per hour. The hours will cancel, and it leaves us with 1.53 times 10 to the 5th seconds. So those are good international units. They're compatible in the meters, kilogram, second system. In terms of center to center distance, R, okay, we're in kilometers. We need to multiply by the fact that there's 1,000 meters per kilometer. The kilometers will then cross cancel and leave us with meters. So we're in good shape there, aren't we? Alright, now another thing we need to do though is to figure out, take this time, well now it's in, take the time in seconds, which is 1.53 times 10 to the 5th seconds for the time, and we need to translate that into tangential speed. So we're going to assume here, to simplify the problem, that this is a nice circle, and we know that a circle has a circumference of 2 pi r. Okay, we know that the distance around is the circumference, and we know that distance divided by time is equal to speed, right? Tangential speed. So if we take the distance, which is the circumference, and divide it by the time, we're going to get the tangential speed. Okay, so let's go ahead and do that. The circumference is 2 times pi times this radius of this big circle here, which we look up here, it's 4.22 times 10 to the 8th meters. And then we'll divide it by the time in seconds, which is 1.53 times 10 to the 5th seconds. Now we'll get the, if I do that with the calculator, I've already done it, we get 1.73 times 10 to the 4th meters per second for the tangential speed, Vt. Oops, I better move it up a little bit. Okay, so now we have the speed there. We're in pretty good shape. We could go ahead then and figure out from using the centripetal force idea. Now, what is providing the centripetal force in this case? You got it, gravity. Gravity, in this case, is the centripetal force. And according to Newton's law of gravity, gravitational force is equal to the universal gravitational constant, okay, times the mass of, let's say, Jupiter times the mass of Io divided by the center-to-center distance squared. That is the centripetal force in this case, so we'll equate that with mv squared over r. Alright. Now if we look, let's try to simplify as much as we can. This mass here is the mass of Io. It's the orbiting mass, so we can cancel that out with this. We see that one of these r's can cancel, and so we're left with universal gravitational constant times the mass of Jupiter divided by the radius is equal to v squared. Okay, well that's pretty cool. We can then now get the tangential speed, right? Or we don't want the tangent. We already know the tangential speed, excuse me. We want to get the mass of Jupiter. I forgot what we were looking for. Okay, so let's rearrange that equation. So that would be the mass of Jupiter is equal to v squared times r divided by the universal gravitational constant. Now all we have to do is plug in our numbers. V, the tangential velocity, is equal to 1.73 times 10 to the fourth, and that would be squared, times the center-to-center distance in meters. Excuse me, let me get the light back on. And I'm going to have to look again what that was. That was 4.22 times 10. So 4.22 times 10 to the 8th meters. And then divide by the universal gravitational constant, Newton's constant if you want to call it that, or the gravitational constant. It's 6.67 times 10 to the negative 11th. I think it's meters cubed. Well, I don't even worry about that because we could always figure that out if we needed to by analyzing the units. Anyway, if you go ahead and do the calculation, you end up with a mass of Jupiter being about 1.89 times 10 to the 27th kilograms. Mass of Jupiter. So that's how scientists know what the masses of planets and stars are. Okay? Alright, so that's one problem. The other problem I'd like to go over briefly is a little roller coaster problem. We have a slick bar of soap right here, so we're not going to have friction, there's not going to be any rotation, and it's on a track, and we let go, and the starting velocity is 0 here, and it's at a certain minimum height that's needed in order to just barely allow that soap to make it around the top of the loop. So we want to find what the minimum speed is, what the minimum V is at the top of the loop in order to just make it around. And the other thing we want to do is find out what the vertical height is. That's kind of a redundant statement, isn't it? But anyway, we want to find this minimum height needed, starting height, so that when we let go, that soap will make it, or barely make it around the top of that loop, and then come out the other side at the bottom. Okay? So that's the scenario. So let's see how to do that. Okay, now in the problem it's given that the radius of the loop is 0.8 meters. Okay, so r equals 0.8. I'll put that there. R equals 0.8 meters. That's of the loop. So we have that. So that's good. And we see that this is going in a circular pattern. So what does that remind you of? Does that remind you of circular motion and centripetal force? What is the centripetal force needed in order to have that bar of soap just barely make it over the top, around the top? Okay, at a minimum speed. Will there be any normal force of the track acting on that bar of soap if it's just barely able to make it around the top? Let's draw a force diagram. If it was going around fast, then there would be a normal force, right? Pushing downward on that bar of soap up here, like that, right? And there would also be the weight of the soap, mg. These two together would constitute what the centripetal force is. However, if we're just talking about the minimum speed needed to just barely make it around the top, then we don't need both of those forces. There won't be any normal force acting on the track, won't be pushing on the bar of soap at all. It'll just be gravity acting on that bar of soap. Okay, so the minimum condition is that the only force acting on that bar of soap at the top of the loop in order for the soap to barely make it around, that's just mg. So this is the centripetal force needed, mg in this case. And we know the equation for centripetal force, and we know that mg is the centripetal force, so let's equate the two together. mg equals mv squared over r. And the bar of soap has a mass m. Notice we don't even need to know what the mass is, because the mass cancels. And so now, therefore, we can figure out what the minimum velocity is, because we set the minimum condition that the only force acting, providing the centripetal force, is gravity. So we have this, g equals v squared over r, therefore v would be equal to the square root of rg. Now r, it turns out, was 0.8 meters, and g is 9.8, so we could go ahead and use the calculator to solve for that. And then we'll just take the square root of both sides. Okay, we get v equals 2.8 meters per second. That's the minimum speed needed to make it around the top of the loop, without, in other words, to complete the circular motion, but just barely. All right. The other thing we need to find is what is the vertical height needed on the track if it is to barely make it around the loop. So we want to find the minimum height h. Okay. Well, to do that, we need to recall the law of conservation of energy, right? And so let's call this position 1 up here. That's position 1. And then up here, this would be probably a good place to put position 2 right there. So that's position 2. There's position 1. Okay? And I'm just going to treat this right here, because we already know what the speed is. That's why I'm using this as position 2. So let's treat this as our baseline this time for our law of conservation of energy. So this is our baseline, our zero baseline. Okay, so if that's the case, then we can go ahead. Remember, the potential energy in position 1 plus the kinetic energy at position 1 equals the potential energy at position 2 plus the kinetic energy at position 2. That's just the law of conservation of mechanical energy. And remember, there's no friction. It's a slick bar of soap. No other forces acting except for gravity. Okay, well, what's the potential energy at the top? Okay, that would be mg and then h min, or h1, I should say. Okay, plus the kinetic energy, hey, it's starting from rest, so that'd just be 0, equals the potential energy at our 0 baseline, position 2, which would be 0, plus kinetic energy, which would be 1/2 mv minimum, which would be at position 2, and that velocity is squared. Okay, well, we see that we have mass here and mass here, so therefore we don't even need the mass, right? So to simplify it, then we get GH equals 1/2 V2 squared. Alright, so we can go ahead then and rearrange. So therefore, we're finding height H1, or the minimum height, is equal to 1/2 V2 squared over G. Let's just go ahead and substitute numbers in now. So H1 equals 1/2. V2 we found out before, remember, was 2.8 meters per second. So I'll plug that right in there. 2.8, but that's squared now, and then we'll just divide by 9.8. So getting the old calculator out again. Oh, I shouldn't have cleared it. I already had that on. 2.8 squared. Okay. Times 1/2 divided by 9.8. And we get 0.4 meters. You go 0.4 meters. Okay. Well, that doesn't seem right, because the loop itself is 0.8 meters. So we need to look and see. Well, that's only the height above the dashed red line here, the baseline. We still need to find the height from the floor. So there's no question about that. You just have to be careful. Okay, so this is H1. H1 being this height here. I hope you didn't get confused on that. So this really isn't H-min. H-min would be this whole height here. H1 is just the little height above the baseline. So we have to add two radii. Remember, the radius is 0.8 meters, so it's 0.8 meters from here to here, and then another 0.8 meters from there to there. So we need to take that 0.4 meters plus 0.4 meters plus 0.8 meters twice. Okay. And so we get 2 meters. So the minimum height above the floor that's needed to allow that bar of soap, if we release it from rest, to just barely make it around that loop, it'd have to be a 2 meter high starting height above the floor here. Okay, thanks a lot, everybody.